Hello everyone, welcome to the lecture number 2 of the lecture series of concepts of efflux. Now we'll discuss a problem related to the topics we have covered in lecture number 1. Now let's see the problem. Beaker full of liquid having 10 meter of height and it is kept on the 10 meter height table. Now you have to find out what is going to be the range of the efflux. That is the problem. Now see, the beaker is kept on 10 meter height table. It can be reduced to equivalent picture of a beaker which is having the total height of the liquid becoming 10 plus 10, 20 meter. And the orifice is at a depth of 8 meter from the surface. So you can draw like this at 8 meter. Now it is easy to find out the range of the efflux. The formula we know from the lecture number 1, that is 2 into root over of h into capital H minus small h. Here small h is the height from the surface of the liquid and capital H is the total height of the liquid column. We can put that. What is the depth of the hole from the surface of the liquid is 8 meter. We'll put 8. Total height of the equivalent column 20 meter. 20 minus 8. That is equal to 2 into root over of 8 into 12, and that is the range of the efflux. 2 root over of 96 meter. Now let's look at another problem. See, this is a beaker which contains rho density of liquid which is having h by 2 height, and below that there is a density which is 2 rho. The height of the column is h by 2, but there is an orifice or hole kept at h by 4 height. So for that you have to find out the velocity of efflux and range. If the column is of h height and we have a hole at h depth from the surface of the water, efflux velocity will be root over of 2gh. But this is applicable, or this formula will only be applicable if the density of the liquid is uniform. We are having only one liquid, then only we can apply this formula. There are two liquids present. Two liquids both are having different density, so we cannot apply this formula to find out the velocity at this point. So how to find out the velocity of efflux? There is only one way, that is the Bernoulli's theorem we have to apply. We will take one point, that is at the surface, and we will take one point at the hole. Now we will conserve the energy. So at point 1, what is the total pressure? Ignoring the atmospheric pressure due to air, we'll consider that what is the potential energy due to this rho density liquid. Rho into g into h by 2. H by 2 is the column height for the rho density liquid, plus we are having also 2 rho density liquid. Above the hole, the height is only h by 4. So we'll write g into h by 4. That is the energy, potential energy of the liquid, that will be equal to entire this energy will be converted to the kinetic energy at this point of the 2 rho density liquid. So the fluid emerging out will be 2 rho density. So energy is 2 rho into v square if it is coming out with velocity v. Then we can solve this. We can find out the velocity of efflux. So see, rho g h by 2 plus 2 rho g h by 4, that is equal to half of 2 rho into v square. So this we can solve. This is rho g h by 2, this is also rho g h by 2. So this is rho g h, that is becoming half of 2 rho into v square. 2 will cancel and v is equal to root over of g into h. That is the efflux velocity. So if rho density liquid is having column height of h by 2, how to convert the density of rho liquid which is having h by 2 column height? What will be the equivalent height if we fill with 2 rho density liquid? See, there is an easy trick. What is the amount of potential energy per unit volume at this point? Rho into g into h by 2. So that should produce in the 2 rho density liquid of same amount of potential energy at the same point. So See, this we can write it as 2 rho into G into H by 4. That means if the density of the liquid is 2 rho, the equivalent column length is becoming H by 4. In this problem, the liquid having density of rho is having column height of H by 2. If we convert it to a density of liquid 2 rho, what will be the equivalent height of the column? 2 rho, it is having already H by 4, and if we convert it to a density of 2 rho liquid, then the equivalent column length is becoming H by 4. Now the problem is reduced to this problem. Now, how to find out the equivalent total column height of the liquid having the only 2 rho density? So we'll convert this column which is having rho density liquid of height H by 2 as well as 2 rho density liquid having column length of H by 2. We'll convert it to a column of liquid which is only having 2 rho density liquid. How to do that? See, the hole will be at this point only, at H by 4 height only from the ground. Now, the above it, 2 rho density liquid is there for height H by 4. But above it, the rho density liquid is there, that is not giving rise to the same amount of column depth below the surface as we discussed. Now, how to convert that? So here, what is the total height? H by 2. So we can write rho into H by 2 plus we can write 2 rho into H by 4. Then we can divide it by 2 rho. That is going to be our liquid column which is having height above the hole. That is our height. So what is that? Rho H by 2 plus rho H by 2 by 2 rho, that is equal to total of H by 2 above the hole. Now see, above the hole there is already H by 4 height occupied by the 2 rho density liquid. Now what is the only thing left? That is H by 4. So we will cover it H by 4. So we will write H by 4 having 2 rho density liquid. So right now the entire this problem is reduced to a uniform liquid having density 2 rho, which is having the total column height of H by 4 plus H by 4 plus H by 4, that is 3H by 4, and the hole is at depth of H by 4 plus H by 4, that is H by H equal to H by 2 depth below the surface. And then what will be the range? Now we can apply this formula of range, that is 2 root over of H into total column height minus H. So here 2 into where H is H by 2 into total column height is what right now? 3H by 4. So we'll, instead of H we'll write 3H by 4 minus we'll write H by 2. Then it is becoming H by 2 into H by 4. It will become H by root 2. That is going to be our range for this problem. I hope you have understood the equivalent column conversion concept. We'll again discuss the same concept in the next problem. We'll keep row, 2 row, 3 row, 4 row, this kind of arrangement we'll keep, and then we'll solve the problem. So that will help you to understand this concept in a more effective way. Thank you so much for watching. We'll meet on the next video.